Assalamualaikum and good morning, everyone. Okay, so today we are going to learn a new topic, a new lecture related to biofluid mechanics. Okay, so this is our last lecture. So starting next week, I hope you guys can start doing your project, and we will do project presentation on week 15, study week, on Monday. Okay, so I've put in column already the announcement for project presentation date. So we do the project presentation on Monday, week 15. Okay, so the reason for doing on week 15 because on week 14 there will be a lot of other presentations. So I don't want to mess the week, okay, with more presentations. And then we will also do test 2 on week 13. So on Friday 21st January 8 a.m. So I will let you know more about this test at the end of this lecture. Okay. Okay, so let's look at biofluid mechanics. So at the end of this lecture, you will be able to understand the application of fluid mechanics in modeling a biomechanics system and solve and analyze various fluid mechanics model of biomechanics, fluid mechanics model of biomechanics using COMSOL multiphysics. Okay, so last week we have learned about solid mechanics, and this week we are going to look at fluid mechanics. So fluid mechanics actually deals with the motion of fluids such as liquid or gas, while solid mechanics deals with the deformation of solid materials like our skin, our bones, muscle, and so on. But for fluid mechanics, usually we will deal with fluid in our body, such as blood, interstitial fluid. So interstitial fluid is the fluid in between cells. So in between cells, there are a very small amount of fluid that that is used to transport all of the nutrients or waste from fluid from the cells or from blood to each other, okay, to remove them or to bring supplies to the cells. We also have lymph fluid ataupun cecair limfa, okay, lymph fluid. So lymph fluid is the fluid that contains apa lymph lupa dah. So it's like a fluid that contains fluid that related to your immunity systems. Okay, I think well, I honestly forgot what is lymph fluid, but in your body there is like all the glands like kelenjar yang dekat tepi leher ni, okay, and then kelenjar bawah armpit under your ketiak. So all of these kelenjars or glands produce fluids, okay, we call it lymph fluid. And also we can study the fluid dynamics of air in trachea, and sometimes we can study drugs, okay, drugs in that we consume in our body. So solving the fluid mechanics equations is very difficult if we solve by hands. So if you take a subject CFD, computational fluid dynamics, you might learn how to solve CFD equations, Navier-Stokes equation, by hands, okay, using numerical methods. And most of the time, it's very difficult um, because of the equation itself, okay. So fluid mechanics equation is actually one of the equation that that still remain unsolved, meaning that if you look at Wikipedia, it's one of the uh, Millennium Prize problems. It's like a mathematical problems that if you manage to solve it, you will get $1 million. And most of the time, fluid mechanics will be solved numerically. And to make it easy, we requires computer software like MATLAB or COMSOL, for example. So in fluid mechanics, we also have the terms like strain and stresses, similar to solid mechanics. So in fluid mechanics, we define strain rate to describe the motion of fluids. Okay, so fluid, we assume it's like particles that are close to each other. So when it moves, one particle moves, it will attract, or it will pull or push the neighboring particles, okay, the neighboring particles. And we use the concept strain rate to describe uh, the forces or the strain in between two particles. So for continuous flow, let a particle of fluid located at some coordinates, and we have the velocity of that particles. And for strain rate, we also have a tensor, or in a matrix form, which can be defined as, so V is the strain rate, equals 1/2 of del V, the velocity, over the del X, okay? So don't worry about the formula. Just want to let you know that the strain rate tensor, V, equals half of the differentiation of velocity over differentiation of the original coordinates. So to describe the fluid motion, we require the fluid properties. So one of the properties of fluid is known as the viscosity. So if a fluid is incompressible, meaning that the fluid, we compress the fluid, but the volume still remains the same. So it's incompressible. And isotropic, isotropic means that the forces between the particles are the same, okay? Meaning that it doesn't act in a specific direction, but the direction of forces are equally distributed. Then the constitutive equation of the fluid is equals this, okay? The stress tensor of fluid equals negative pressure times identity matrix plus mu. So mu is our viscosity, the fluid viscosity, times the strain rate, okay? Strain rate tensor. So usually for a Newtonian fluid, we assume the viscosity as a constant. But in real life, some fluid doesn't behave like a Newtonian fluid. It will behave as a non-Newtonian fluid. So a non-Newtonian fluid, the viscosity might change with temperature, for example. So that's a different topic. But in this lecture, we assume that all of the fluids are Newtonian fluid. The concept of viscosity can be understood using a simple case of shear flow in a uniform velocity gradient. So it's like viscosity is like it makes the fluid to when it moves in a cylinder or in a tube, it will move like it will behave like a sticky things, okay? So it doesn't flow smoothly because the fluid will stick to the wall of the tube, okay? So that's why the velocity profile as shown here, it doesn't produce a uniform velocity profile, but instead it produces a uniform gradient, okay, velocity gradient, or the velocity profile has a triangular shape. Okay, example here is a triangular shape. So when it comes to fluid, we have two types of fluid motion. So we have laminar flow and also turbulent flow. So when fluid in motion has a strain rate that remains constant with time, then the flow is steady or laminar. So for laminar flow in a tube, we can consider it as a series of sliding tube to represent the fluid motion. So for a laminar flow, the velocity profile will look like a parabolic. And if we can illustrate this using a sliding tube, it will show it will look like this. Okay, so the motion of fluid will look like this figure. So we also have a non-laminar flow, or we call it turbulence flow. And the difference between these two flows depends on the Reynolds number, okay? Reynolds number of the fluid flow. So usually a Reynolds number less than 2000, the flow will behave as a laminar flow, while Reynolds number more than 2000, the flow will behave as a turbulent flow. So a turbulent flow will have a velocity profile that is not exactly as a parabolic. Okay. Okay, so let's look at the equation of fluid mechanics. And this is the equation that I explained just now, the constitutive equation for incompressible Newtonian fluid. And this is the strain rate tensor. And if we substitute this strain rate tensor into the constitutive equation, we get the constitutive law of the fluid equation of motion. Okay. So the equation of fluid mechanics, the fluid flow equation, here it depends on the viscosity of the fluid. Okay, so the final equation here is also known as the Navier-Stokes equation. So in this lecture, I'm not going to go on details about how to solve Navier-Stokes equation, how to derive the Navier-Stokes equation, but I want to show you that for fluid mechanics model, that a model that involves fluid mechanics, the equation will be the Navier-Stokes equation. So in this Navier-Stokes equation, we are solving for the fluid velocity U, and also the pressure, the fluid pressure P. So there are two things that we are solving at the same time, the velocity and the pressure. Okay, so that's basically about the introduction about fluid mechanics. Let's look at an example of how we can apply that on COMSOL multiphysics. So consider the following simplified model of descending aorta, thoracic and abdominal aorta. So aorta is our blood vessel that brings out blood from the left ventricle or the left heart. Okay, so aorta is the biggest blood vessel, and it brings blood to all of the body except the lungs. Okay, and if our aorta is damaged, then our body or our body tissue will not receive enough oxygen or blood supply from the heart. So in the aorta, there are two parts. Okay, there are parts that going up, usually coming from the heart. Okay, so it will go up first, and then after that it will go down. Okay, so the going up part, we call it the ascending part. So this is, let's say, our heart. So this is our aorta. So this is the going up, and this is the going down part. Okay, so it's like a gelong. a loop. And the going up part, we call it ascending iota. And the going down is, we call it descending iota. So there are two types of iota, thoracic and abdominal iota. So thoracic iota is the part of aorta near to the heart, while our aorta actually very long. It goes to our abdomen, okay, our badan. So the lower part, the near to the abdomen, we call it abdominal aorta. Okay, so there are two types of aorta. Basically, it's a one aorta, but we separate the section into thoracic and abdominal. And in this question, solve the model in COMSOL and plot total blood flow against time for an input half sign pressure pulse. Okay, so the input pressure PT is given by this equation 120 sine 2 pi t for time 0 until 0.5. And for the other time, we assume pressure equals 0. And the diameter of this iota is 20 millimeter. The length is 30 cm. And at the outlet of the iota, we apply this electrical circuit model. So this circuit, I explained back in lecture number 2, okay? I think week 3. So we call this Winkelson model or lump parameter model. So we have the capacitor represent the aortic compliance, while R resistor represent the resistance in the aorta. And assume the viscosity of the blood in the aorta equals 3.5 millipascal times second, and the density of 1000. And assume at time 0 the blood is at rest, okay, doesn't move. So we can do this in COMSOL multiphysics. So this is the step, and this is an example of the results, okay. So after we do the simulation, we will get this kind of results. Okay, so let's do the tutorial. Okay, so firstly, we start by choosing model wizard. Okay, so in this example, we are going to use, we assume that the iota as a cylinder, okay, just a straight cylinder. But this iota, because of the cylinder shape, we can solve this using 2D axisymmetric instead of using 3D. Okay, so the reason why we choose 2D axisymmetry is to make the simulation a lot faster. Okay, so if you use 3D or to solve a cylinder, it might take more time. Okay, and also more RAM from your computer. So we choose 2D axisymmetry. And then after that, we can choose the physics laminar flow. So to find laminar flow, you can go to fluid flow in a single phase flow, laminar flow. Or if you cannot find it, you just type laminar flow in the search, okay? And then click add. And go to study. So we choose time dependent study. So the reason why we choose time dependent study, because the pressure just now, the input pressure is depending with time. So we choose time dependent and click done. Okay, so we can start by drawing the geometry. So because we are doing this simulation in 2D axisymmetric, so we are not going to draw a cylinder, but we are going to draw the cross section of the cylinder. Okay, so we can draw a rectangle. So before that, from the tutorial, we need to change the default unit. Okay, so from here, because the unit is in the geometry is in millimeter, we can set the geometry unit to millimeter. And then after that, we draw the cylinder, the rectangle. So the width is 10 millimeter and the height is 300 millimeter. So we get the cross section of the cylinder. So when this rectangle revolves about this red line here, it will become a cylinder. Okay. Then we have drawn the geometry. So we can define the parameters. So here in parameter 1, you can define the parameter given in question. For example, viscosity is 3.5 millipascal times second. Okay. And then the density 1000 kilogram per meter cube. And then we can define the Winkelcell model parameters like compliance 2.75 and put the unit. And the resistor. And also the maximum value of the inlet pressure. Okay, so when we define all of these parameters, then we can start by defining the inlet pressure. Okay, so we go to definition, right click variables, and we define the inlet. Okay, so we go back to the equation. So P inlet equals 120 sine 2 pi t when time is 0 to 0.5 second, and pt equals 0 for the other time. So we can use if else to define this and write if else in console. So to write if else, so you simply write if. So if t less than 0.5, then the pressure P inlet will equal P max times sine of 2 times pi times T. Okay, so when times less than 0.5, then P inlet will equals P max times sine 2 pi T divided by 1 second. Okay, so the divided by 1 second is to make sure that the the value inside the bracket here has no unit. Okay, so we divide some unit because time here has a unit second, so we remove the unit. Okay, by dividing by 1 second. And then if time not less than 0.5, then P inlet equals 0. So in if else here, there are 3 things that you need to input. Okay, so the first input is the condition. So in this case, when time less than 0.5. And then the second input is what happen if time is less than 0.5, what is the value for P inlet? And then the third one is what is the value of P inlet when time is not less than 0.5. So it equals 0. So we have three things here. So in case if you have a different if else, then you can put it this way. So be reminded that in this if else here, we only have two if, okay? If t less than 0.5 and if t bigger than 0.5. So if you have three conditions, you cannot do this using this method, okay? And that one is something different, okay? Tak keluar exam lah. Okay, so after you define your P inlet, then we can define some other things, okay? So in the tutorial, it defines the some integration, okay? So we go to definition, components coupling, integration, and then we choose the bottom rectangle here. Sorry, change the domain to boundary, and then choose the bottom line here. Okay, we choose the bottom line here, and then uncheck the compute integral in revolve geometry. Okay, so the reason why we want to integrate is later on when we want to calculate the flow, okay? The flow of fluid going out from the cylinder, we will need to use some integration, okay? So this is asking you or actually create some integration of something on this boundary that you highlighted here. Okay, so after we define the integration, then we can set the physics. Okay, before that, we need to calculate the flow, okay? Okay, so in variables, you need to calculate the flow. So we name it flow as Q. So in the flow, it measures the flow of fluid about this line that you highlighted just now. So we need to integrate, okay? So flow equals the integration of area times velocity. So integrate area. Okay, so firstly, velocity. So velocity is negative W, negative because it's going downward, and times the area. Okay, so the area is 2 times pi times r. So 2 times pi times r means the circumference of the cylinder. Okay, so when you integrate the circumference, you will get area. Okay, that's the purpose of integration. So you integrate the circumference, you will get the area of the circle or the cylinder a cross-sectional area. Okay, so 2 pi r. R here is the r of this length of this line that you highlighted. Okay. Okay, so we have done setting the variables. Now we can go to setting the physics. Okay, so firstly we go to fluid properties. So we need to define the density. So we have defined previously in parameters. So we just put the name rho. Okay, so in parameters 1, we have defined rho here. So in fluid properties, you just input rho. And then in the viscosity, dynamic viscosity, we have defined previously mu, okay, mu. And then we need to define the inlet. So by default, there is no inlet given to you. So you need to choose from right click, inlet, or you can go to physics tab on top and go to boundaries, inlet, okay. So from the inlet, the tutorial says apply on the rectangle, top of the rectangle. So this is the boundary of inlet, because the bottom one just now is the outlet. Okay. And then change the boundary condition to pressure, because we want to apply pressure at the inlet. And in the pressure, you just write the pressure that you have defined just now, P inlet. And then uncheck this suppress backflow. And then you need to define the outlet. So again, right click, choose outlet, or you can go to physics tab and choose outlet. Okay. So for the outlet, you choose the bottom boundary, and then change the pressure boundary condition to pressure, and then the pressure equals P out. Oh, P out tak define kat sini. Okay, P out. So okay, sorry, P out. And then suppress backflow. Okay, so your P out will be in yellow because you need to define it elsewhere later. So continue the tutorial. So from the question, as I shown just now, we have this circuit at the outlet. Okay, so your pressure will depends on the circuit. Okay, so you need to define the equation for the circuit in console multiphysics. So how to do that? Dalam tutorial dah ada. So we go back to physics and just add new physics, and then go to mathematics and choose global ODEs and DAEs. Okay, you can find this by searching as well. Okay, type it in the search. And then in the global ODEs, you go to the global equation. Then you can write the equation for the Winkelcell model or the circuit. So it's already given in the slide. So just write it out. Okay. So P out equals, so copy paste. Okay, so we need to change the unit first. So the dependent variable, we change to Pascal. And then for the source term, we change to meter cube per second. Okay, so when you change this, then the yellow will becomes black. Okay. And then okay, and then after that we can go to study one time dependent and change the range. Okay, so it might take some time. So in my laptop I want to change the mesh. Okay, because it will take I think more than 5 minutes, I think. So I change the mesh to, of course. Okay, even ni mesh ni pun macam banyak. Okay, but later you can try using normal mesh. Okay, so after we set the time range, then just press compute. Okay, so the simulation has finished. Then we can do some analysis. So from the tutorial, you need to plot the total blood flow against time. So meaning that you need to plot Q versus time. Okay, so using 1D, so you plot flow. So flow is Q, and just plot flow against time. So you get this graph. Okay, and then from the slides, uh, the the 2D plot, you can plot the velocity. So if you go to velocity, no, this one. So the plot is slightly different because of the mesh that you use. Okay, that I used just now is coarser. So to get similar results, you need to use a normal mesh. Okay, I think you will get a similar results. Okay, so that's it for today's lecture. Uh, you can now do assignment number 6, and the due date I don't remember. It's in Kalam. So now you have 3 assignments. Okay, that you need to submit: assignment 4, assignment 5, and assignment 6. So all of this assignment we will discuss on week 13, Thursday. Okay, just before your test the next day. So if you have any question, you can.
Doktor,
Yep.
saya nak tanya soalan assignment question 4. Assignment 4.
Okay.
Kan ada buat abdomen, electrode and hati kan? Kalau nak define dia punya conductivity tu, dia tak boleh select asing-asing. Macam dia akan explicit one terus. Jadi macam mana nak asingkan hati tu daripada abdomen?
So awak kena tambah satu lagi electrical conductivity ke apa.
Saya dah tambah tapi tak boleh select. Dia akan select semua sekali terus. Lepas tu saya
Okay.
try paste. Dia akan explicit one juga. Dia
Okay.
macam ada difference ke? Kena buat difference ke apa ke dekat benda tu?
Tak ada, just awak lukis satu sfera je dekat dalam 4 segi tu. So you just draw this cube, rectangle, and then just draw a circle, a sfera. And then bila define, by default dia akan ada satu, so if you go to physics, AC/DC, electrical current. So by default, you will have one current conservation. So you define the material, let's say for domain number 1. Okay, and then you add one more current conservation. So this new current conservation, you just choose the heart. Okay, so maybe sebab heart tu dekat dalam, so
Dia akan
awak tak
select
boleh nak select, susah nak select, betul tak? So cara select dia, you can just point your mouse to the nearest location, nearest to the heart, and then just scroll. Okay, scroll your mouse. So when you scroll the mouse, dia akan highlight only the heart inside the rectangle. So try first.
Scroll ke dalam masa.
Contohnya ada macam mana nak lukis. Contohnya gambar ni lah. Okay. So just point your mouse here. and then just scroll. Okay, scroll your mouse. Then dia akan highlighted the heart. Okay. Boleh kot. Josh dapat buat.
Ke
Dapat
pakai selection, pakai selection pun boleh tuh kalau tekan automatic.
Tak tahu.
Lepas tu dia keluar nombor 1 dengan nombor 2 je tu. Lepas tu pilih nombor 2.
Awak boleh pakai selection ni, betul. Selection ni just type number 2 for example. Then when you click OK, dia akan highlight number 2. Oh, not this one, sorry. I think here kot, paste selection number 2. Tu George dah ajar dah. Pagi-pagi George dah ajar orang.
Thank you, Doktor and Judge.
Okay.
Untuk yang
okay.
mesh tu pula sah, dia ada 2 tu.
Okay, untuk mesh, you can just right click and choose. In your case, it will be free tetrahedral, okay, sebab dia 3D. So in this my punya console, because I'm using 2D, so I choose free triangular. So for your 3D, it's a free tetrahedral. So in this free triangular, go to the geometric entity level ni, and then go to domain, and then repeat the same thing. Just choose the heart. Okay, just choose the heart. So let's say selection number 2, boundary number 2, and then after that, in the free triangular or in the free tetrahedral, in your case, right click, choose size, and then just change normal ni ke final. So you can try first by build selected. So when you build selected, you will see the heart will have a smaller mesh. And then after you manage to mesh only the heart, then you can try build all. So when you build all, you will see that the heart will have smaller mesh, tapi the abdomen, the body will have bigger mesh compared to the heart. Okay, so you just choose free tetrahedral, and then in the domain, pilih the heart, and then right click free tetrahedral, choose size, and then choose the mesh size that you want.
Okay, saya faham dah.
Okay.
Thank you, sir.
Okay. Ya kot. Tak apa. Josh dah buat dah. And then for the parametric sweep, I think you can refer to lecture last week. I forgot. I think last week's lecture. So you just choose parametric sweep, and then just add the parameters. So you define the distance of the ground electrode using symbol D. So define in this parameter. So let's say D equals 0. And then in the parametric sweep, you can just choose D and put the range here. The range given in the question. Okay. So this one, the solution will take quite some time because it solves for many values of D. So bersabarlah masa solve tu. Okay, any question before we end this lecture? Okay, so please refer to Kalam for the due date of the assignment, and see you again week 13 insyaAllah. Assalamualaikum and goodbye.
Thank you,
Thank
sir.
you, Doctor.
Thank
Thank you,
you.
sir.
Thank you.